So this is the 2009 Scholarship Physics paper, question number 4, and we're looking at a loop-the-loop where we've got a ball rolling down a track and it does a loop presumably and goes off into the distance. We've been given the formula for the rotational inertia of a solid sphere, and we've got a ball of mass m rolling without being slowed by friction, so that's our clue that it's assuming ideal conditions. Without being slowed by friction, it's going down a ramp leading to a vertical circular track. Capital R is the distance from the centre of the track to the centre of mass of the ball. The radius of the ball R is much less than R. Okay, so before we do the question, let's just consider what that comment means. Small r, the radius of the ball, is much less than R. I think that means we can assume that capital R is as the diameter. It's the diameter of the track to the centre of mass of the ball. So we can pretty much ignore small r, is what it's getting at, and capital R is all our consideration we need to worry about. So A, explain what will happen to the ball for a release height where the height is less than or equal to the radius. So if we just sketch that on here, roughly, that's our radial height, R there. So our height of release is going to be less than or equal to. And we have to explain what will happen. What will happen? This is very much like, I think it was one of Newton's thought experiments, where you drop a ball and under ideal conditions it'll go to exactly the same height on the other side, and then it'll just come back to the other side. And with ideal conditions, no friction, no loss of energy, it'll just maintain that, going back and forward at the same height on both sides. So this situation is pretty much the same. So the ball will roll down, it'll maintain contact with the track. If it was to go above the vertical, it can't in this situation when it's being released from a height less than or equal to r, but if it was to go above the vertical, there are two things that would happen. It would either run out of puff and fall off, or it would carry on right round. But we're not worried about those situations. So one thing you might be concerned about, if you remember your consideration of rotation and rotational kinetic energy, is that as this ball increases in, it starts off with gravitational potential energy, and then it increases in rotational kinetic energy and linear kinetic energy. So you might think that because you're gaining rotational kinetic energy, that there's not going to be enough energy to bring it back up to the maximum height over here, which is the radius height. But it doesn't matter. That it will go up to there, because it will, remember, as it's increasing up this side, it will slow down. So that rotational kinetic energy will come back to kinetic energy and gravitational potential energy. So everything that you put into it from the initial gravitational potential energy will come out. The only effect that the rotational kinetic energy will have is that it will cause the absolute lower, the maximum velocity down here at the peak will be a little bit lower than it would be if it wasn't rotating. Okay, and there's a question later on that deals with that too. So now B, we have to show that the ball will loop the loop, stay in contact, that is, with the track for the full circle. That's a nice little hint. If the ball is released from a height greater than or equal to 2.7 r. Okay, so the condition for that is that at the top where it stays in contact, because it's at the very top where you would think, this point here, where you would think that it would has to maintain at least the bare minimum centripetal force to keep it turning. And that's the force and there's the acceleration. So the bare minimum would be when the centripetal force, mv squared over r, equals mg, mass times gravity, for that mass. So mv squared over r equals mg. So that's our condition, and we're going to use that a little bit later. So what are we looking for? We're essentially looking for a formula that'll say H equals 2.7 R for this exact condition. So how are we going to do that? As always, energy considerations are best to use in here. So at this initial height, which will be different from twice the radius, remember this is going to be twice the radius here, that initial height has to be greater, because if it's still rotating here, then you've got rotational kinetic energy. So let's consider all the energy. As I was saying, we've got mgh over here, the gravitational potential energy, and that's where the total amount of energy. And then on the right hand side, once it's at this position, you've got again a certain amount of gravitational potential energy, but in this case it's not h, it's 2r, so it's mg2r. You've also got, because it has a linear movement, you've got linear kinetic energy, which is just our half mv squared, and we're going to have to come up with an expression for v squared, most likely rearranging this formula. Because that has r, we have to make sure that's a capital R as well, otherwise we may confuse ourselves. And as we said before, it's still got that rotational kinetic energy, which is half I, the inertia, omega squared. So the rotational version of the kinetic energy formula. So we're going to have to deal with the velocity here, we're going to have to deal with the inertia here, and we're going to have to deal with the rotational velocity, the angular velocity. So to do that, we've got the v squared I think we can deal with over here. So if we rearrange the formula above, we can get a v squared. Well, first of all, the masses will cancel, that's an easy one. So we've got v squared equals rg, or gr, depending on how you want to look at it. I don't think it matters at this point. So that's one substitution that we can take. We also know the rotational inertia formula given above is 2/5 gosh, I can't remember. Always go back to mr squared. Okay, so 2/5 mass of the, and remember r is capital R in this case. Is that right? No, it's not. It's small r squared. Okay, so that's going to substitute in over here, and we've got omega squared, or omega, and if you remember from your linear to rotational conversion, omega equals the linear velocity divided by the radius, or the velocity, linear velocity is omega r, and that's going to work out quite nice, because for omega squared, that's v squared over r squared, and I can see already that that small r that we were trying to ignore before is going to be cancelled out by the small r squared over here. So anyway, let's plug all these in. We're also going to have to substitute this formula, so we're doing a lot of substitution, but we're going to have to substitute this formula into here for the sake of that velocity again. In fact, we might rewrite it as omega squared equals rg squared over r squared. In fact, we didn't need that squared because v was already squared. That's nice. That makes it easier. Makes it work good. Okay, so let's put it all together into an equation, since we're getting shorter on time. Back to our orange. So we've got the mgh equals, the first was mg2r, which was the gravitational potential energy at the top of the track, plus the half m, and this time it's v squared, which as we saw up there was r times g, rg, plus, we'll try and keep it all in the same, plus the rotational kinetic energy, which is half I, where's I? I was 2/5 mr squared, so 2/5 mr squared times 2/5 m, and which r was this? Is this small r or is this big R? This is small r because it's the rotational inertia of the ball, and we've also got that velocity, because just to make this a little bit clearer about what we're dealing with there, this is the half, this is the inertia, so from here to here, and now we've got the omega squared part, which will be our rg over r squared. Whew, awful looking big formula, but so much of this is going to cancel out. So let's go right ahead and do some cancelling out. We've got the r squareds cancel, that's great. You'll notice all the way through this, every single term has a gravitational term, so we can cancel out G, 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 and I have to shift it across just a fraction to reach it, and G here. We've also got a mass term, so we can cancel out the masses all the way across there. And I think that, well, okay, the half and the 2/5, so the half will cancel out with the 2 on the top, leaving just a 1. So this is looking messy, so let's rewrite this out. On the left hand side we've just got H, which is what we're hoping for, equals 2R plus 0.5 R, so I'm writing it in this form because it's going to be a nice little calculation, plus 0.2, which is 1/5 R. And you can see all of this adds together lovely in a lovely way to give us 2 plus 0.5 plus 0.2 is 2.7 R. Okay, so that gives us the height, the minimum height necessary for the centripetal force to keep it turning. So to maintain the velocity of the ball as it's looping, to keep that centripetal force high enough to keep it on the track. If the height is higher than this, then you will get an increase in that velocity, which will be enough to keep the centripetal force. An extra force will have to be added by the track, reaction force, but it'll still work. So there we go, that was awesome. Great big, long, tricky mathematical thing, but quite cool.